guys, welcome to the Homework 7 video tutorial. So there were some questions on that last night's homework that really should have been reviewed largely, like 41 and 45. This one was covered by the video I gave you, but they did some shenanigans with the angle theta and exactly where they put it. And also something about the way that they asked the stuff may have come off as a little bit strange to you. It was basically the conical pendulum question that was covered in that video, however. So, before I just tell you exactly how to do this, I should tell you go look again at that video if you haven't already watched it. Alright, now, if you have already watched it and struggled through this question, then this explanation should hopefully help. Alright, so kind of like we did in the video, some of the y forces involves gravity, so mg minus the vertical component of the tension. So they explicitly ask you, what is the vertical component of the tension? And that's all they want, is just exactly that. So we don't even actually have to use a trig function there to solve for the vertical component of the tension. All right, it's just mg. That's what it's going to be. All right, now we will come back to that and which trig function to use in a minute. For the x forces, we have the centrifugal force, so mv squared over r, and then the horizontal component of the tension. All right, to get that one, we've got to plug in, let's see, the speed that they give us, which is, they don't actually tell you the speed. Okay, so we're going to have to figure that one out. All right, and then, okay, so it seems like actually we don't have enough information right now to just plug stuff in to get the horizontal component. So I guess the time when we figure out which trig functions to use is right now. Okay, so Ty, well, that would be the vertical component of the tension. But because of where they gave you the angle from, the vertical component is the cosine function, because it's the adjacent side. So Ty equals mg, but that means that t times cosine theta is Ty. And if that equals mg, then you can find the tension by taking mg divided by cosine theta. All right, now if I want to know the x component, if I already know what the tension is, t sine theta will give me the x component of the tension. So actually, I guess you should use the vertical equation to find the y component directly, all right, and then divide by cosine to get the overall tension, and then the sine function to get exactly what the horizontal component of that tension is. All right, I'm not going to worry about the numbers for this video, so you can plug in as you see fit. All right, for the centripetal acceleration. All right, now centripetal acceleration, or excuse me, they say the radial acceleration, which is basically centripetal acceleration, just in the opposite direction. That is v squared over r. So if I look at my x equation here, I've got tx equals mv squared over r, or t sine theta equals mv squared over r. Well, v squared over r is the acceleration you're looking for, the, quote, radial acceleration. All right, so same, really, as the centripetal acceleration. All right, so that means that it's going to be t sine theta divided by m. That's it. That's all you got to do for it. So you didn't actually explicitly have to find the speed. Although, if you did find the speed, then you could plug back in here. All right, so by asking it this way, they were actually being kind of nice because they didn't make you then also figure out the radius. the radius would be L sine theta, because it's the side opposite to that angle. So if it did come up for this kind of a layout, the radius of the pendulum bob's motion would be L sine theta. All right, next question. For the car going over the speed hump, at the top position, right, when it's at the very top of the speed hump, the three forces that are acting on it are the normal force, gravity, and centrifugal force. All right, well, if this is a circle, I suppose, or it's a circular arc it's going through, that would make the centrifugal force upwards, because it's got to go out from the circle. All right, so part A, where they want to know what is the normal force, you're going to have the sum of the vertical forces is N plus Fc minus mg equals 0. Plug in the numbers, solve for the normal force. Okay, where, as usual, Fc is mv squared over r. Part B of this question, though, where it wants to know the maximum speed that the car could have without becoming airborne, we have asked that one before and answered it, right? At the top, given that the forces are all in those various directions, the maximum speed is found by setting the normal force equal to 0. The idea there being the faster you go, the smaller the normal force is going to be, which you can get from solving this for n, right? It's mg minus Fc. All right, so the faster you go, the larger this Fc term is going to get, and therefore the smaller the normal force will get. Well, there's a limit to how far that can go. At a certain point, the car leaves the ground, and the normal force has to be 0. All right, so you find the maximum speed by setting the normal force equal to 0, and at that point, this equation just becomes that right there. And if you then move the mg over and plug in your numbers, you will notice the mass cancels. Don't care what the mass of the car is for part B. And you should get that the maximum speed is given by the expression square root of gr. Plug in the numbers, figure out what the maximum speed is. All right, 45. Again, this should be largely reviewed the way this is done. So I will draw, I'm not going to plug in any numbers for this. I am going to draw in the forces, though, because that's key to parts B and C and also D. All right, so three forces would be tension, gravity, and the centrifugal force. So that's what those will look like for the top position. At the bottom position, gravity is, of course, down, tension is up, and the centrifugal force is down because it goes out of the circle. All right, so at the top, you would have an equation that looks like mg plus t minus Fc equals 0. At the bottom, the signs would switch around. You'd have mg plus Fc minus t equals 0. Okay, so everything else from there is just based on plugging in the numbers that they give you. All right, now the one somewhat of a quirk on this one is part D. Usually when we're asked a question about a maximum speed, we set something equal to 0. That's not the case here. The reason there's a maximum speed is because the string snaps. So nothing is set equal to 0. Rather, you plug in the maximum tension of 22.5 newtons. And based on that, you get that there is a maximum speed it can have before the string will snap. All right. Another question they could ask you, but they didn't, would be the minimum speed that the ball or whatever has to have at the top. And that will be based on setting the tension equal to 0, kind of like we did up here with setting the normal force equal to 0. All right, they didn't ask that, but that would be a good question for this kind of a circular motion problem. All right, let's see if we can find the last one. And, happy Halloween, everybody. Guess that's Mipula. Oh, here it is. Number 54. All right, so this one mixed together the concepts that you had on homework 5, that worksheet, where you had 2 connected objects with centrifugal force. So it was a little bit more involved, okay, but we still follow all the rules of what we've been doing so far, right? You draw the forces on each of the objects. All right, so there's most of them. All right, we have tension inwards, and we have centrifugal force outwards on the mass number 1. All right, and then on the hanging mass, we've got tension and the weight of the object. Okay, so now that we've drawn in all of our forces, step 2 is we've got to write all of the force equations. So for the hanging mass, it's going to be T minus m2g, or the other way around, since they are telling you that it's at equilibrium, right? The fact that this thing is spinning up here is what's holding that thing in place. Okay. All right, so that's it for that one. M1. All right, for M1, we could write in stuff about like N and M1G, but we don't care about the normal force because there's no friction. Friction is not part of this question. It's just the tension and the centrifugal force that we end up caring about. Right? And again, it's staying in that circular path, so we act as though it's an equilibrium question. All right, add these together, and what you're going to get is Fc minus m2g equals 0. So Fc, that would be this mass, so m1 v squared over r minus m2g equals 0. All right, so fine. Let's actually answer the questions that were asked. What is the tension? Well, the tension is m2g. All right, what is the centrifugal force equal to? Turns out the centrifugal force also equals m2g. All right, because that's what the tension is, and these two are balancing out to keep it moving in that circular path. All right, now, what is the speed? All right, so that's where we have to actually do what we just did here, right? I set up my 2 equations and added them together so that the tensions would cancel out. And now, if I solve for v, I'm going to get that v is, let's see, m2g r over m1, and take a square root. All right, so that is my expression for the speed of the object. All right, now based on that, if I increase m2, the speed of m1 would have to grow greater in order for it to stay moving in that circular path. So that's what they mean. All right, then for if we decreased m2, it could move more slowly and maintain its circular path. So what that, practically speaking, might mean is it would move out a little bit. Right? The radius would increase, and that's how it would end up slowing down. Okay, I hope that was helpful.